apologize. I'm very late and it seems like we don't have as much time left. I normally go over, but I do have a meeting after this, so don't worry. I'll make a note of it and you won't be penalized. If I cut you off or I interrupt, I don't mean to be rude. It's just to tell you that time is up. So let's get started. Does that sound okay to you?
Yeah, that sounds great.
All right, perfect. Let me go ahead and paste the problem. So given n as a part of an n by n two-dimensional array, print all possible paths where you can only go down and right. A single right move is represented by the character R, and a single down move is represented by the character D. Each path is a string of moves from the top left to the bottom right of the input.
Gotcha. Okay, cool. So I have some clarifying questions. Do all the paths have to be unique?
Yes,
Yes. Okay. What is the lower bound of this n that we can be given?
1.
One. Okay, gotcha. What about the upper bound?
Upper bound will be 50.
50. Okay. And so I just want to clarify, if we're given the dimension n, so like an integer, that's the parameter input. That's not the actual matrix that we're given.
Yep, that's correct.
Okay, so integer n is given, not actual matrix. Got it. Okay, so I'm going to open up the drawing mode. So say if we have like an n of 3 or something, then to make sure I got this right, and I'm going to draw an absolutely terrible 3 by 3 matrix. My lines are perfect. Then essentially we want to print all the paths from the top left coordinate, so row 0, column 0, to the bottom right coordinate of 2, 2 in this case. Is that right?
Yep.
Okay. And I have one last question. Is there any special formatting we need to print all the paths?
What do you think?
I think that perhaps there can be like a new line between each. So you can have like one path, whatever it may be, with the right and down moves, and then a new line, and then you continue on from there.
Okay, yeah, that'd be fine.
Okay, cool. So starting off the logic. So in this matrix, I notice in the description, there's a pretty big constraint that from the starting coordinate or from any other coordinate, you can only really move to the right or downwards. It's only those two moves. So taking a gander at this matrix, it's not too far-fetched to say that, the only way to get to this cell, again, from the source cell, the starting coordinate, is to take one single right move. You can't go down to reach this cell because at that point you'd be at row -1. That's not a thing. We're given a 3 by 3. So I'm just going to take a note of one, that there's only a single path that can be taken here. And I think expanding on this idea, if we took a single right move to get here, we can do a similar thing, a single right move to get here. So in total, you would have 2 right moves for a total of 1 move, because there's just one way to get here. From here, it was the 2 rights. That, to me, manifesting in code, that does sound like a for loop of some sort for the first row. And on that note, we can do something very similar for the first column, or technically the 0th column, where from the source cell, you can take one down move to get to this cell. And from there, you can take another down move. You get DD to get to the this cell, in which case it would also take just one way to get there. These feel like sibling for loops to me, one after another, and to kind of tie together, we start on the top left coordinate, so I feel like we can just put a 0 there because that's where you start. You don't take any moves to get there. That makes sense so far to me, but my next question is, what about the inner matrix, right? So taking a quick step back real quick, I feel like it may seem like I'm going off course because I'm trying to figure out the number of paths that get from the top left to the eventual bottom right, when I know that I'm trying to return the actual path representation from the top left to the bottom right of the input, as the description says. But I do think that it's helpful to compute the number of paths, and then with that core logic and anything that goes with it, layer on the requirement of, hey, now we need the string representations. So basically, I'm taking it one step at a time and kind of breaking it down. So continuing this thought on the inner matrix, which seems like a nested for loop, on this first cell, this first iteration, how many paths are there, unique paths to get to this cell? Well, it seems like there's 2, in which case 1 will pass through this cell from the top. So if you're going from the top, you're going down. So that's one way. And then from the left, it's a similar vibe. You take another way to get there. So I feel like if you add these two and kind of build off of the paths you've already determined, you can figure out the number of unique paths, in which case 1 plus 1 would be the 2 for these two. That does make sense to me. So if we move on to the next iteration, you can apply very similar logic. 1 plus 2 is 3. So there are 3 ways to get here. And to prove it, there's one way right here from the top, and then 2 ways from the left. So yeah, I think if you add them, the 3 will represent the 3 unique paths. So, for these last 2 iterations, you add 2 plus 1 to get 3. And then lastly, you have 3 plus 3 to get 6. So there are 6 paths. So now, part 2, where you kind of layer on the path string representation, how would we find the path string itself? Well, if we go back to the very beginning, once again, obviously there's no path to be taken here, but we know the coordinate to its right has one string path, and it's a single right move. So it would just be a single right move there. And recall, this is a singular for loop. So on the last iteration of this loop, you'd obviously be going to the right until the for loop ends. So you append a right to the current path of right to go to the last column, in which case you'd have RR. And to do this in code, obviously whenever you go to the right, you do a column plus 1 to advance. So that's the end of that for loop. You can dispatch a similar one to go downwards, where if you go from, a single empty string to go down, then you tack on a D to get to this cell. Of course, it takes one down move to get there. Similarly, on the last iteration of this for loop, add on another D to get double Ds to go to this cell. So after that, as for the inner matrix, we can do something super similar, where on the first iteration, you look this time from the top and from the left. So one at a time. At the top, you have a single R, that's how you got there, but now you want to take a down move. So you're going to suffix a D to get RD. You look at the left, and if you look at the left and you came from the left, you know for a fact that you're going to go up in the opposite direction to the right. So if you add a right there, then you get DR. Amazing. That makes sense to me for these 2 moves, the 2 possible moves. You move on to the next iteration where you do something very similar, but here I notice there's going to be a modification in our code where if you look from the left, for example, I realize this is a list of strings. You can have multiple ways to get somewhere, right? So we're going to have to loop through these 2 possible strings. And again, if you're going to the right, you want to tack on an R, in which case you get RDR and DRR. And then for similar logic, if you look up top, you add a D because you're going to go down from the top. You get RRD for the 3 unique paths. So that makes sense to me. You're just filling out the rest of these. On this iteration, you look up top, you tack on a D, so RDD, DRD, and DDR from the left. And lastly, this will be a lot of writing, but it's going to be RRDD. And I apologize if I make any typos, but you kind of get the idea. You have DRRD. Then you have the other 3 RDDR. I'm just going to write it out of bounds now. DRDR. And lastly, DDRR. I think that's good. So I think that's the general idea, is that if we have paths that have been, pre-computed, pre-stored, we can avoid redundant calculations and kind of build off of those determined paths. And in this case, to eventually get the 6 unique paths, that's our answer, in string form, of course. So to make this all kind of possible in code, I know I'm given just an n of 3, like I clarified. But to make this work, I would need to instantiate like a whole 2D matrix of the n by n to store the actual string paths themselves. And then at the end of the inner nested loop, of our matrix, I can just simply loop over the list of strings, as I determined, in the bottom right cell at row 2, column 2, to just print everything out. So on the first iteration of that for loop, you'd have, of course, RRDD. You have the new line, then you just go on with the other 5. So, all right, I feel like I can codify that. Can I translate this into code?
Well, are there any other solutions that you'd consider?
You're so screwed. This is what you get for only memorizing the DP solution. You know they don't ask for DP. Right. So another approach, definitely. I feel like, I could simulate this whole logic that I had described with DFS, with a DFS call. So essentially with recursion, forward, to try and get to our base case at the bottom right, but then backtrack whenever we hit some base cases. I'm not sure what those are yet, but I'm thinking, that wouldn't be as efficient because I'm not building off of these, pre-existing calculations, but it would work. It would be functional. So I think going through a kind of a pseudo dry run, if I'm starting at the top left coordinates and I'm simulating DFS here, obviously we want to go to the right or down. I think in code, I don't think the order matters, but I'm going to prioritize and bias towards going to the right first because why not? How that works is, again, you're going to add 1 to column, but you also want some sort of path variable to build off of. I don't have that 2D matrix to store all these strings anymore. So you have some sort of path variable to which in the first iteration, you have an empty string. You're going to add an R to that because you're going to go to the right from the 0th column to the first column. You'll land with a single R. So as per recursion, you're going to keep doing that same thing until you can't anymore. You'll terminate with a base case. But until then, you're going to keep going to the right, appending an R to the path variable. Again, column plus 1 from the 1 to 2 makes sense to me. You're at this coordinate now with RR. Okay, and here's where it gets slightly interesting. You can add another R to RRR, but hold on, you're at column 3. So here lies the first base case in which if your column, or row for that matter, is 3 or exceeds 3 for some odd reason, then you're out of bounds. You want to backtrack. So for that base case, we simply return, go back to where you are, and then you can do a row plus 1 to go down. So you go to the right as much as you can till you can't. Then after on the backtrack, you're going to go down. So to go down, again, like I said before, to reiterate, you add a D to get RRDD, or just RRD rather. You're going to go to the right, but hold on, you are out of bounds. You're going to backtrack, and then you're going to go down, tacking on a D to be in this coordinate with RRDD. But you don't want to keep going. So here is the second base case where in the code, it sounds like if you ever are at a row of 2 or n minus 1, in a column of 2, again, n minus 1, this is n by n, then you reach the bottom right cell. That's how you know. In which case, you're going to print it out then to get right here, RRDD. And then there you go. I think from there, you backtrack up, then you backtrack again, you backtrack again, and then you're going to go down to get RD. You go to the right to get, where is it? RDR. And then you're going to go down, tacking on a D to get RDRD. You print that out, new line. And I'm not going to go through the rest of it because it's quite redundant, but I feel like that makes sense. Great. Can I code this out?
Yes.
Okay. Awesome. Okay, so for the code, let's call this, for accurate verbiage, we're going to print something out, and it's going to be unique paths. So let's call it print unique paths. There could be multiple, of course, like in our example. We're given just an n, again, non-natural matrix, like I said on line 18. So without, you know what, and let's write an inner function. Let's call it backtrack. It's going to be our DFS function that I'm going to call from the print unique paths. It's going to take in a path variable for the DFS, as well as a row and column, and not implementing that yet. I know for a fact I'm going to call this with a path of an empty string, as well as a row of column of 0. So in the backtrack, what do we do first? Well, like I said, to simulate the workflow, we're going to keep going to the right. And if you go to the right, you're going to tack on a right move because you're going to the right. So that seems right to me. Column +1. After, on the backtrack of that, after you hit some base cases, which I will code out shortly, I'll do something terrible. And we'll then, after that, prioritize going down with the down move, in which case you're not going to add 1 to column. You're going to inversely add it to the row to go literally one row deeper. As for the base cases, there were 2. That the first one we saw, this is Python. So if the row is equal or greater, and I don't think it'd ever be greater because you're only incrementing it by definition is 1 by 1, but I'll just choose to be defensive. There's a trade-off. Or if the column is out of bounds, so in this case 3 or more, you're simply gonna return because you're gonna be out of bounds. I don't want any errors. So after that, what if you hit the very end, the bottom right coordinate, in which case the row is going to be n-1, and so both booleans must be true, the column n-1 as well. So if that's the case, you're going to print out the current path that you have been building this whole time. And I do want to note here that in Python, the print function does include the new line. So it just works out that way for sure. That is my implementation. Can I do a dry run to make sure this all works?
No, that won't be necessary.
Okay, cool.
Can you tell me what the time complexity is?
Right. That's totally a thing, right? So to start things off, we found, I found all the possible ways to do something, which is super vague, but in this case, I'm finding all the possible paths, right? So to me, I feel like that's the definition of permutations. So as an example, if we have RRDD here as a possible path, with permutations, the order matters. Oh, so that means each R and each D is treated irrespectively very different from their counterpart R and D. So let me show you. Here's an example. This can be represented as R1, the first right move you make in this matrix, as well as R2, the second right move you make in this matrix. Same thing with our down moves, D1, D2. However, here's a different ordering that makes this whole string apparently unique because it's permutations. You can have R2, R1, D1, and D2 remain the same. This is considered different from one another in that if you make a right move, and sure, you make one again, the first one could be R1, in which case this has to be R2 or vice versa. But nope, I feel like that's not right because these two possibilities have to fold. They basically have to collapse into a single RRDD. I mean, I see from here, there's only one RRDD. There's not 2 of them. So I guess what I'm saying is it's actually not permutations. It should be something where the order doesn't matter, which sounds like it should be combinations. And I think overall that's because in the requirements, line 15 says we need unique paths. The order shouldn't matter. We want to have it be unique, a single RRDD, not duplicates, in which case the arrangements produce multiple, duplicates, right? Okay, so I feel like I'm on the right track. So if we're trying to find all the combinations, then kind of breaking this down, I feel like the first thing to look at is how many moves does it take to get from the top left to the bottom right? And we can generalize kind of this formula of course, first of all, it would take 2 rights and 2 downs, no matter what you do. Yeah, no matter what you do. So breaking that down, how many right moves do you have to make? It's obviously 2, or in other words, n minus 1, right? Because if you take 1 right move here and you take 2 down moves, you're going to have to make the second right move sooner or later. So n minus 1 R moves, that makes sense. Likewise, you want n minus 1 down moves. The same logic can be applied. And if you add these together, that'll give you the total number of moves that you'll make. So these are coefficients, 1n, 1n. So what's 1n plus 1n? That's 2n. What's negative 1 minus 1? That's negative 2. So right here, I think it's very important. 2n minus 2 is the number of moves you have to make to get from the top left to the bottom right. So if I kind of a jump, but if I take the factorial of this number, then that's not right. I guess that's the permutation again, not the combinations, right? So if I plug in 3 into this equation, I get 3 times 2 is 6, minus 2 is 4, factorial. That is 4 times 3 times 2. That's times 1. That's 24. So there's 24 possible ways to get from the top left to the bottom right. But like I said before, that's not right. The issue lies with the duplicate paths. We only want the unique ones, these 6, not the 24 that we had computed here. That's not right. So if I take this example with RRDD, the question is how many duplicate paths must we exclude if each move is distinct, right? They're different from one another. So to take this as a full example, you have 4 slots, right? For the 2 R's and the 2 D's. Obviously, for the first choice for the R, you can either have R1 or R2. So sure, let's say it's R2. Then for the second, if it's R2, you only have 1 choice. So that's R1. So that's basically 2 times 1 options, right? Or in other words, more generally, that's n, that is n minus 1 factorial. 3 minus 1 is 2. 2 times 1 is 2. For the D, the same deal, right? You can rearrange it only 2 times 1 ways, in which case, sure, it could be D1, D2, which on that note, there are 2 ways to rearrange R, but there's also 2 ways to rearrange D. So looking up here, I could have R1, R2, same as this guy, but you'd have D2, D1, the opposite of this. And this is another permutation. Similarly, you could have R2, R1, D2, D1. So basically there are 2 ways there too. 2 times 1 again. So more generally, that's n minus 1. The same thing as with R factorial. And if you multiply these together, that will give you the 4 ways that these can collapse, these duplicates, into a unique path. So if I just, as a sanity check, pass in n of 3 into this equation, that's 2 factorial times 2 factorial, that's 4. That's true. There's 1, 2, 3, 4. Okay, so basically to exclude this algebraically, I'm going to divide the total permutations here by those duplicates, by n minus 1, I hope I have space, factorial, times n minus 1 factorial to get, we saw this is 24. We saw down here is 4. If you divide that, you get 6. This represents the 6 unique paths, and that's the time complexity here, right? That's the 6 right here. 1, 2, 3, 1, 2, 3, 6. Yep. That would be the answer. And this is really interesting. I think this is the multi-set, a permutation of a multi-set where you're dividing by multiple different characters that can be rearranged themselves, the R and D in this case. But I feel like that's the time complexity. But in relation to the code of what's happening, we do. Oh, okay, I came back. Kinda. I think a lot of things went wrong. That's odd, but we'll move on. So basically, we're still building the path on each and every iteration, right? And the length of each path in the worst case would be 4 characters. It'd be generalized kind of, 2 minus 1. I think I had it up here. It was 2n minus 2 factorial. The 2n minus 2 is the longest path that any string can kind of be, but also the number of moves you can make. Because if you're here, you're tacking on another d, you're doing that to a 2n minus 2, generally, in theory, string. So that just boils down to just big O n for the time complexity that you'll tack on to this big equation that I'll awkwardly rewrite like so. Great. So that's right here. That's the time complexity. For the space complexity, that would also be 2n minus 2, right? Because again, it's the number of moves that you're making that correlates with the recursive stacks you'd ultimately recruit. So in this one that we kind of dry ran, it's 4 stack frames. 1, 2, 3, 0, 1, 2, 3, 4, 1, 2, 3, 4. So it would be 2n minus n, which would be generalized to just n. So this is the space complexity, and this would be the space complexity, kind of weird like that. Yep. So yeah, that would be the number of recursive frames stacks that we'd maximally have in our DFS. There we go.
Nice. What if you had to return all the paths and not just print them? What would change in the code?
I see. So you wouldn't just... Okay, I see. So we're not printing them out anymore with, a new line and then et cetera, et cetera. Okay, so that's interesting. So immediately as the modifications to the code, I feel like I gotta rename the function, but I'll get to that if I can. I definitely need a result list of some sort to hold the paths. Oh, all the drawings came back. Great. Thank you, CoderPad. A result list like that, to which to add it, no longer just print it. Okay, so that makes sense. I feel like the base case would change when we get to the very end, the bottom right cell, bottom right coordinate, that whatever string that you have, or RDD, you would print it out, but instead you append it to this result list, which makes sense to me. I think that's the only change in the backtracking function. And then afterwards, you would have to return it. So this is no longer a void return type. You return this result of the then populated unique paths. Yeah, so I'm going to code that out. That sounds like it makes sense to me. So instead of print, it's going to be called get. Let's see. So we have another base case. But before that, let's instantiate the list. I called it result. Sure, I know for a fact, before I forget. Let's return it. So return result. And then I think the last change would be to, instead of printing it out, like I said, we're going to simply, to our result, append that path. There we go. I feel like that makes sense to me.
Thank you for that. I got everything that I needed. For this next part, I'll just verbally ask you. What if there were some obstacles in the grid?
All right. Okay. Interesting. I have some questions. I'm going to scroll down real quick in this coder pad like so. Okay. So first off, how are these obstacles represented?
It's up to you.
It's up to me. Okay. So, well, first off, I assume we're given a 2D matrix now, kind of opposite from before, not just end, so that the 2D matrix's value can represent obstacles. Okay, so maybe it's an integer matrix with ones as obstacles and then zeros are not. So I guess extending that, I'm assuming that these obstacles are not passable. Like we can't traverse past them.
What do you think?
I think so. Okay, cool. So ones are not passable by the nature of being obstacles. That makes sense. Okay, so moving on to the coder pad drawing mode, I'm going to scroll down just a little bit. Definitely learned my lesson from before. So if we have a smaller matrix, say like an n of 2, and I'm going to draw this terribly. of a 2 by 2, then obviously maybe we can have, sure, an obstacle there. That means inversely, the rest of these are zeros, but I'm not going to show them because I need stuff in there. We can still use the DFS algorithm and pretty much reuse the bulk of our algorithm. But the difference is there are now ones, which are obstacles. So just going through the motions, because I'm not sure how the code looks right about now. You have a single empty string at the top left coordinate, from which you'll go to the right. Okay, but here there's a new base case. Before, sure, if you went out of bounds, you got to stop and backtrack and return. But here, it's a 1. So we got to extend that base case that, hey, if you're out of bounds or you're on a 1, you can't traverse through that. So you're just going to very quickly go back. After that, you're going to bias towards going down with a down move like we did before. If you append a D, you're going to get a single D, from which you go to the right to get DR. And of course, on every one of these checks, you'll be like, am I on an obstacle? No, you're not. So you can just keep on going. So here, the same base case exists, just like the previous problem. You're at the last row and column, in this case of the 1, 1. So you're going to add it to that same list, the same list that I named results. This is our answer, and this is what we would return. So for the time and space complexity, I feel like that's the same as before, but I'll talk on that more. Can I try to decipher this into code?
Yes, please.
Okay, cool. So really quickly, I'm going to scroll up and copy and paste the previous problem because I'm going to extend it. Don't want to modify it. So I think, first of all, this should be called get unique paths with obstacles. That is verbose, but at least that's descriptive to me. The other change is we are given a matrix that's called grid, but we still want n for line 43, line 45, and so forth to work. So n still remains to be in this n by n, a length of the grid that is sensical, that's logical. And the only change that I did call out was if you're out of bounds in terms of the right or the column or where you currently are at the row and column is a 1, you want to return. You can't go through it. There are obstructions. I don't think anything else makes, or at least requires changes. May I do a dry run to verify that this code works?
Mm-hmm.
Okay, I'm going to use the same example because I don't want to spend 50 minutes. So on the first iteration, actually before that, line 39, we make a single result list. Line 40 says that n will be 2. That makes sense. You enter the backtrack on line 51, pass in a row of 0, column 0 on the first iteration. Line 43, are we out of bounds or at a 1? No, this is a 0, first of all. We don't hit the second base case on line 45 either, and thus we do not execute line 46 because we're not at the bottom right coordinate. So as always, on line 48, you're going to recurse to the right, appending a right move to the current path variable to get, R. On this next DFS call, you do it all over again on line 43. We do actually execute this because the Boolean is true. We're at a 1, so we return line 44. We go back, in which case we're backtracking to line 49, where you'll go down, adding 1 to the row from 0 to 1 on that new iteration. Line 43, as a base case, are we on a 1? No, we're not. Are we out of bounds? No, we're not. Line 45 says, are we at the bottom right cell? Also no. So you're going to keep going. Line 48 says you add a right to go to the, the right. Where on this DFS call, you do hit the base case on line 45, where you append this to the list because you're at the last row, last column. Here it is. And then you're going to backtrack from there, where you're going to go down and realize you're out of bounds on line 43. You're going to backtrack up to the first cell, which you're done. You're past line 49, and you backtrack from there. You get out on line 51 and return the result on line 52. This is indeed our answer. But as for the time complexity, which I want to talk about more, I actually have a question. Is it possible to not have obstacles at all?
Mm-hmm. It's possible.
Okay. So in which case, I want to finalize it. The time complexity is the exact same as before. in the worst case where you don't have any ones, you just have zeros, again, it boils down to just the original problem.
Perfect. And the space complexity?
Right. So the space complexity, it'd also be the same.
Okay, for this next part, I just need a verbal explanation. What if you were given this 2D matrix with ones and zeros? How would you find the shortest path from the top to the bottom?
Okay. So I'm going to write more notes because that's how it is. So to clarify, it's a single path that we must return, and it has to be the shortest path. Was that what you said?
Yes.
Okay. Is it still 4 directions that we can move in?
It's 8 directions now.
It is 8 directions. Okay. So that means its diagonals count as well. Okay. So I'm going to scroll down for the last time, and sure, let's do an n of 4. So So it'll be a 4 by 4 matrix. My lines are perfect, like so. So it's of zeros and ones. So maybe we have ones here again as obstacles. You have zeros and all the rest of them. Right. Okay. So just thinking about this immediately, I feel like if you want the shortest path, previously, we used DFS and that was great, but I don't think that's as applicable here because although we want a single path, we want the shortest path, which will be guaranteed with BFS, in which case, because it's breadth level, breadth first search, the moment you get to the bottom right, that will be the answer, the path that we want. So even if you use something like level order traversal, this would be the first level. This would be the second level because now we can go diagonally. Then you have the third level and lastly the fourth level. And by the time you get to the fourth level, you know for a fact that when you get to this cell and you pop in, process it, it should be containing our answer, our path, our shortest path for a diagonal in this case of the 4 levels for the 4 moves. So kind of talking about how this would work, and before I mention that, if the top left or the bottom right coordinates are 1, then we know for a fact that this is not possible. And that's 2 edge cases that we can consider. We would just return something, maybe -1 or something, or an empty vector, empty list in this case. Okay, but talking about this more in depth, as with BFS, you'd have some sort of queue, in which case you'd have the row, column, but newly you'd have the path as well of where you currently are. So you would see this queue with the top left, right, of where you would be after you check that one edge case of a possible 1 in the path of manually 0, 0, makes sense to me. Then, and you don't have to use level order, you can use regular BFS, which on the first kind of loop of this, you would add these 3 cells. So I can kind of coordinate that a little bit. So you have this one right here, which is row 0, column 1, and you'd have a path of 0, 0, but also you can add on the current one, 0, 1 as well. And you'd add these 2. So let's do that real quick. You have row 1, column 0, copy 0, 0, as well as the 1, 0. My handwriting is perfect. And then you have the 1, 1, which case you also have the copy 0, 0, and you copy. So, okay, so this is not very efficient, but it might work. 1, 1. Then you pop this guy, and then you go on with this BFS logic until you get to the bottom right, in which case when you pop it, you return the list that you would have, and that'd be the answer. I will say though, this time complexity is very slow, and I think we can do a lot better. So what's better would to be use a map solution of some sort.
I'm sorry to interrupt you, but it looks like we're a bit short on time, so we can do a quick question and answer with the remaining time we have left.
Okay, yeah. All right, sounds good. So I'm wondering what org you're in, because a friend of mine is in the tadpole team, and that sounds super interesting.
All right, here's the feedback that I would submit for Minh's interview. So overall feedback indicates that the candidate displayed impressive problem solving, bug-free code, strong Python skills, and clear communication, asking for clarity when appropriate. Extensive documentation was also provided in the form of inline comments as well as diagrams. Thus, no verification was required. However, the candidate failed to compare multiple solutions and their respective trade-offs for the first medium problem. The candidate wasted a significant portion of time going over the dynamic programming solutions before being explicitly prompted to consider other non-dynamic programming approaches. When explaining the time and space complexities, the candidate showed in-depth knowledge of mathematics. An MLE role may be a fair path to suggest given the candidate's prior background. Feedback indicated that though the candidate fully answered the medium follow-up question, they failed to solve the second follow-up due to time restraints. It should be noted that I was slightly late, and given the candidate's sharp reasoning skills, no negative signals are counted towards them. When compared to other candidates, the decision was made to move forward with the candidate. Thank you for joining Minh and I for this mock interview today. I hope y'all have a great week. See ya!